Hi, welcome to StatStuff. I'm Matt Hansen. This lesson is part of an extended series on hypothesis testing in the analyze phase. In this lesson, I'll review the one proportion test that's used when comparing one proportional type of metric to a standard value like a goal or a target. I'll spend the first part of this lesson reviewing some of the critical concepts that can help you to understand how to use this test. But despite that, I recommend then that you at least review the prior lessons on hypothesis testing if you haven't already done so. But for now, let's review again why we even need hypothesis testing.
Well, we need hypothesis testing because, remember, our goal for the project is to resolve the problem by first building a transfer function. We don't want to just alleviate the symptoms that we're seeing, but we want to get to the root cause. You may recall my example of my daughter Hannah. We don't want to just alleviate the arthritis pain that she was feeling in her leg, but we want to heal the root cause, which was the strep throat. So if we don't know what the root cause is, then that means we need to build a transfer function to figure that out. By building the transfer function, we can know what changes, that is, what improvements that we need to make that should fix that root cause. Now, if you recall, the transfer function is defined as y equals f of x. That is, the output response of y is a function of one or more input x's. It's part of the IPO flow model, again, that we described before in the IPO flow model, where we have an input that leads to a process and an output. Well, the y refers to that output. The process piece refers to the function that's applied to an x, the x being the inputs that are part of it. So it's really expressed in the IPO flow model to an equation. Now, how does this transfer function fit with hypothesis testing? Well, hypothesis testing tells us which of those x's, which of those inputs that we're looking at, are independently influencing the y, the output metric. When we reject a null hypothesis, we're building evidence proving which x's are guilty of driving the y. And what we'll do at the end is we'll compile all the evidence in the improve phase of DMAIC, and that's when we'll begin to fix those root causes or come up with a plan that's going to fix those root causes. Now that we know from the hypothesis testing which of the x's are the most critical x's that have the most influence and where we need to make the biggest changes that are going to affect our output y.
Okay, now let's review again the various steps that we follow when doing hypothesis testing.
On a high level, the steps begin with a four-step process, which was starting with a practical problem. We're stating the problem as a yes or no question, and then we want to convert that problem into a statistical problem. That's going to help us to figure out which is the right statistical tool or method we're going to use to help figure out how we're going to do the analysis. And then we apply that statistical tool or concept on it, and then we interpret the results from that and come up with some analytical answer. And then from that, we would interpret the analytical answer into some practical solution or some practical way in applying that so it would make sense to us. And at the heart of doing the hypothesis testing, again, for steps 2 or 3, that's where we drill down to 6 additional sub-processes or sub-steps in order to figure that out. So it started off with defining the objective. Then we want to state the null and the alternative hypotheses. Then we define the confidence level and the power levels based off of the alpha and beta risks that were identified. Collect the sample data, and we want to calculate the p-value. All these are part of building this statistical problem. And then once we've done that and run the test, then we interpret the results. This is going to be the point where we decide whether we're going to accept or reject the null hypothesis. This is what we'd follow when we want to go through the formal hypothesis testing.
All right, now let's review again the chart for finding the right statistical test and where the one proportion test fits into all this.
Well, since the set of tests we're looking at are for proportions, the one proportion test fits over here within our whole drill down. This is because the data types that we're looking at, we're assuming like the y and the x are both discrete values. And because of that, we're doing tests of proportions. And the example that we're going to look at is more specifically when we're doing a comparison of one value to a standard or to a target or a goal. That's going to help us know that we need to follow this particular test where it's a one proportion test.
Okay, before we dive into this test, let's review again what I mean by proportions.
Well, proportions are measurements with using discrete values, and they're generally going to be represented as a percentage. So even though they are percentages and percentages are numeric, they're not to be confused as continuous values. So just be careful. There could be some risks if you're using percentages or measures of proportion for some tests that are really designed to be used only for continuous values. So just be aware of that risk that might be there. Now, defects and defectives are the measurements we might use for measurements of proportion. So as an example here, we have 5 different units, and each of these dots represent represent an opportunity per unit, and the red dots represent a defect that might be within each unit. Well, based off of from a unit perspective, we might say, well, 4 of these 5 units are a defect because they have at least one of these opportunities that's a defect. So in that case, the DPMO measurement we might use is 800,000 or 80% defective. Or however, we might say from a defective perspective, that is, how defective is each unit, and if there's 9 opportunities, in this case there's 2 defects. In this next unit there's 3 defects, and so on. From a defective perspective, how defective each one is, we might say the DPU is 1.8 based off of the total number of opportunities and the number of defects we have, or it's 20% defective. Now, why are statistical tests needed for proportions? Well, simple proportions using percentages, they might be insufficient. If you're just comparing a percent to another percent, that may not be complete. You have to really account for the level of confidence that you can have in those percentages, because you may not be able to trust the raw numbers. So as an example, you might have 50% proportion of 100,000 records. Well, that's going to be very different in the implication than if you have 50% of only 100 records. So you have to account for the difference in the sample size, which could affect the overall proportion, which ultimately affects the precision of the proportion that's represented.
All right, now we can dive into actually showing how to run this one proportion test in Minitab.
Well, when should we use this actual one proportion test? Well, it's when we want to compare one proportion value with a standard or a target or a goal or something like that. And how do you find it in Minitab? Well, you go to the Stat menu, select Basic Statistics, and select one proportion. So the inputs that you might see for this type of test, you'd get a dialog box that looks like this from within Minitab. And then you plug in here the portion that's being measured, that is something like the number of defects, and then you have the total number of samples that you'd be plugging in from which the events were that you were measuring. And then the hypothesis proportion down here would represent the actual standard or target that you're comparing it to. You might select options as well, and you get this additional dialog box if you want to set a separate definition for the confidence level, and if you also want to define this alternative here to help do the comparison.
Now let's walk through a couple examples of the one proportion test. First, we'll start with an example of measuring repeat calls at a call center.
Well, as background information for this example, we'll say that it's a call center that's in Phoenix, and they want to know if they're meeting their goal of 60% of their calls not having a repeat call within 2 days. They sampled 130 calls and found that 82 of those 130 did not have a repeat call. Now, the raw percentage of 82 out of 130 is 63%. Now, does that 63%, does that statistically prove that they've met their goal of 60%? So we have to ask ourselves as a practical problem, do the 82 out of 130 sample calls prove the Phoenix call center is meeting their goal? Well, for the statistical problem, we'll first start off by stating the null and alternative hypotheses. The null hypothesis would be the proportion is less than or equal to 60%, and the alternative is that the proportion is greater than 60%. So practically that means if the goal is met, then we're going to expect to reject the null hypothesis, and we'll accept the alternative hypothesis of proving that the goal was met. Now, we're also going to define the confidence level and power levels. We're going to use the defaults, as we will in most of these tests, where the default of 5% for alpha risk, which represents a 95% confidence, and 10% for beta risk, which represents a 90% power level. Now, we're going to type out the problem in Minitab, and in Minitab we're going to go to Stat, Basic Statistics, and one proportion. We're going to select Summarize Data, and we're going to type in 82 for our number of events and 130 for the number of trials based off of the data in this sample. And we're going to check the box to perform a hypothesis test, and we're going to type in the goal of 60% or 0.6. Then we're going to click on the options and ensure that the confidence level that we want is 95% based off of what we selected earlier, and we're also going to select the alternative as greater than. When we run that, we're going to get a certain output from Minitab that's going to look like this. And in that session window, we're going to interpret it this way. The p-value over here is greater than 5%, or 5% risk that we want. So in this case, we fail to reject the null hypothesis. By failing to reject it, that means we did not meet the goal after all. The 95% lower bound is a confidence interval. So what does this mean? Well, basically means that from a lower bound perspective, our confidence interval would represent down to 55, almost 56%. That's how low that we actually could be. The population mean among all the calls that are handled within Phoenix, even though the raw sample came back at 63%, it could be as low as almost 55 or 56%. And because 55 or 56% is below 60% as our goal, that would mean that we have a 26% or almost 27% risk of failing. In that way, we would say we don't have enough confidence, we don't have enough data to prove that we actually had met the goal. So the formal conclusion, or from a practical solution, we might say is the sample that we have, that we looked at for these 130 calls, that sample is insufficient to prove that the Phoenix call center is meeting its goal of 60%. So why is it that this happened, and what is it we can do to change the results? Well, if we collected more data and ran this test again, we probably can find for sure whether we were meeting the goal or not. So even if we did 10 times as many calls in our sample, we got it up to 1,300 calls, and we got up 10 times as many at 82 here. If we reran those numbers, the raw number will be 63%, but again, having more samples, we're probably going to make our confidence interval more narrow, and by making it more narrow, we're going to get this 95% lower bound closer to the 60%, and because of that, we're probably going to end up proving statistically that we've met the goal.
Now we'll walk through another example in using this test when measuring billing quality.
In this example, when we're looking at billing quality, we'll say the background is a billing department has a goal of 98% accuracy for customer bills, which each have multiple opportunities for error. So we take a sample of about 1,000 bills, and of the 1,000 that were sampled, we found only 17 errors. So we want to ask ourselves, as a practical problem, do the 17 out of the 1,000 sampled bills prove that the billing department is meeting their goal? Well, it looks like they are based off of just the raw percentage, but is it really from a statistical perspective? So first we're going to state the null and alternative hypotheses, where the null hypothesis is the proportion is less than or equal to 98%. The alternative is the proportion is greater than 98%. And what does that really mean? Well, if the goal is met, we're going to expect to reject the null hypothesis, and we're going to accept the alternative hypothesis, which would prove that they've met the goal. Now again, we're going to use the same confidence and power levels here as we had before, the default of 5% alpha risk and default of 10% beta risk. And the information we're going to type in the Minitab is going to look like this. We're going to go to first the stat, basic statistics in one proportion. We're going to select the summarized data, and then we're going to type in 983 for a number of events and 1,000 for a number of trials. And why is it that we use 983 instead of 17? Well, because in this case what we're measuring for is the number of successes. Since the actual percentage that was given is based off of accuracy rate and not based off of defect rate, we're just changing our number using the 1,000 minus the 17, and we're going to use that as our number of events. We could have done the opposite, but in this case we did it this way in order to be consistent to the original accuracy measurement of 98%. So based off of that, then we're going to check the box to perform the hypothesis test, and we're going to type in the goal of 0.98, which was our goal for the accuracy. And then we're going to click the options button, and we're going to make sure that we have the confidence level of 95% as our confidence level we identified earlier, and that the alternative is set to greater than. And then from a statistical solution perspective, here's the output that we would see from Minitab. And what does all of this mean? Well, the p-value again is going to be much higher than our 5% risk we were willing to accept. So in this case, we failed to reject the null hypothesis. And the 95% lower bound for a confidence interval is listed here as well. And just as we saw in the prior example, this 95% lower bound for a confidence interval falls below our 98% target. Because of that, it looks like there is a chance that we could, or at least a 30% chance that we could have the actual full data set fall within or fall below the 98% goal that we have, and because of that we're going to fail to say that we've met the goal after all. So what happens if we use 2% as our goal with the 17 errors instead of the 98% with the 983? Well, we're going to come out to the same exact results. It's going to come out to the same exact p-value. It's not going to be any different, and we would just get the inverse for what we're showing here for our confidence interval. But by looking at the p-value, it's not going to change, and we're going to come to the same exact conclusion. So from a practical standpoint, the way we'd interpret this is we'd say the sample is insufficient to prove that the billing department is meeting its goal of 98%. And what do we want to do if we want to change that or figure out why this even happened? Well, again, we may not have had enough samples. If we merely get more samples, increase the sample size, it's going to shrink the confidence interval, make that more narrow. And by shrinking that, then we have a better chance of really proving more precisely whether we hit the goal or not. But based off of the samples that we had collected, it's just insufficient for us to really prove statistically that we met the goal.
All right, before we close this lesson, let's discuss how we can apply some of these concepts in a practical way.
I'd like you to refer back to the critical metric, the output Y, and the 5 factors that we're using for all of this hypothesis testing. And for any factor that is a percentage value, try to apply the one proportion test that we reviewed in this lesson. Now to do this, you'll need to compare that factor with a goal for that particular factor that's typically set by your organization. Other factors in your organization can be used for this exercise as well, but let's see if we can at least use the ones you've previously identified for this hypothesis testing. So before you run the one proportion test on your data, first ask yourself, does the factor meet or exceed whatever the goal is? Then after running the one proportion test, ask yourself, does the factor statistically meet or exceed the goal? Now if the answers to those previous 2 questions are different, then how does that affect how you typically measure and communicate that factor within your organization? So as an example, does that factor, meeting or not meeting the goal, affect any financial decisions, like how people are being compensated or any other costs? Or maybe any process changes, for example, how the process may need to be modified, or maybe some other critical actions that are taken. If so, then how should the results from this one proportion test be used to help influence your organization? Should they change how the goals are being set for that particular metric, or should they change how the factor is being measured, or should they change how they react when they compare the metric to that goal?
Well, that wraps up this lesson. Check out StatStuff.com for many more resources that can help you achieve powerful results. I'm Matt Hansen. Thanks for watching.